Assalamu alaikum, dear students. So we meet again, and today this is our lecture number 2. I do hope that you enjoyed, and more than enjoying, you understood what we talked about as an introduction to semiconductor materials and the devices that we fabricate from these materials. In this lecture, we will be mostly talking about the charge carriers, how we introduced extra charge carriers in intrinsic semiconductor materials, that is how we make doped semiconductor materials. And then we would talk about the approximation known as effective mass approximation, in which the electron mass has to be modified to account for the existence of electron moving in a real crystal rather than moving in vacuum. And finally, we will talk about the density of states and Fermi-Dirac distribution function. And of course, you would appreciate at the end of the lecture or during the lecture as we go along that distribution of charge carriers in semiconductors, that is, the carrier concentration is highly temperature dependent, not only in the pure semiconductor material but also in the doped, that is extrinsic semiconductor materials. And finally, we will discuss another very important topic, that is generation of electron hole pairs in semiconductors as well as their recombination, because both these processes are required to bring back the semiconductor material in equilibrium. So this was a slight overview of what we are going to discuss or talk about in this second lecture. Before I begin with my lecture for today, let's quickly revise what we talked about in lecture number 1. So here is a brief summary. We classified semiconductor material into mainly two groups, namely the elemental semiconductor materials, then intrinsic and extrinsic materials, and finally the compounds made from group 3 and 5, 2 and 6, and so on and so forth. And we also touched upon briefly in our previous lecture the applications of these materials into various devices and their operation depending upon your requirement. So again, we repeat, we memorize, or we revise our memory of lecture number 1. What are semiconductor materials known as intrinsic semiconductor materials? Well, intrinsic semiconductor materials, mostly we had been talking about silicon, so today again I will make silicon as my reference material. In pure or intrinsic semiconductor materials, as you would appreciate today, they are not doped, and that's why they are termed as pure. Then how do the electron and holes come into being in pure semiconductor materials? Well, at this point, the most important mechanism is that I'm going to discuss about is thermal generation. Of course, there are other processes that generate electron and holes in pairs, but we will postpone that discussion for the later stage, maybe in this lecture or some other lectures in future. Today, I will give importance to thermal ionization, that is thermal generation of electrons and holes in semiconductor materials. Let me remind you or stress the point that this thermal ionization process takes place not only in the intrinsic material but also in the doped or extrinsic material as well. So coming back to this present slide of intrinsic semiconductor material, what happens in the intrinsic semiconductor material? Well, as we elaborated in the previous lecture, even in the pure material there are electrons and holes generated by thermal generation process. What has this term thermal generation process got to do with this topic? As we mentioned in the previous lecture, a semiconductor is in thermal equilibrium, and the reference temperature we had taken and will be talking about in future lectures too, that's the room temperature, 300 Kelvin. In a minute, I'll give you a slide, I'll show you a slide in which thermal energy has been calculated numerically. Well, at this temperature, which is room temperature, electrons are gaining some thermal energy from the system and continuously breaking the covalent bonds. So valence electrons, there are 4 valence bonds in each silicon atom, and as these valence electrons gain energy at room temperature, bonds start breaking. What does this give us, or what happens during this breaking of bonds? You get a free electron from valence band to conduction band. The electron, when it reaches the conduction band, is termed as a free electron. The vacancy left behind, or the bond which has been broken now, is termed as a free hole, and this, in terms of energy band diagram or covalent bond diagram, is termed as a free hole which resides in the valence band. Now we talk about extrinsic, that is doped semiconductor material. You would also appreciate that in silicon there are a total of about 10 to the power 22 atoms per unit volume per cubic centimeter. Obviously, we would like to add dopants. Why? Because we want to increase the carrier concentration from the pure material or the intrinsic carrier concentration. Your intuition would be that let's enhance the dopant concentration as much as we like. But that cannot happen, because if you do that, if you increase the dopant concentration to the level of the host silicon crystal, then you will end up destroying the silicon crystal structure itself. That we do not want. We want the properties, crystal structure and the properties of this silicon material to remain as they were before doping it. So dopant level has to be much smaller than the intrinsic host silicon material. So a rough figure would be that only 1 atom in 1 million atom of silicon will be sufficient. So if you add 1 atom in 1 million atom of silicon material, what you are doing, you are not really damaging or changing or destroying the crystal structure, silicon crystal structure. So even though 10 to the power 15 is a very high number, but compared to 10 to the power 22, it is only 1 part per million or 1 part per billion, so on and so forth. So the typical dopant levels can vary from 10 to the power 14 to 10 to the power 18. At this point, I will introduce another term, another terminology, that is the degenerate and generate semiconductor materials. If you do not want to delve into very complicated mathematical equations and keep the doping level low so that usual equations of thermodynamics are applicable, that is termed as a non-degenerate semiconductor material. So in our lectures, for most of the time, we will be dealing with dopant impurity concentration, which does not make silicon a degenerate semiconductor crystal, or in other words, we deal with non-degenerate crystal or dopant impurity. Finally, the carrier concentration, as I just explained, is highly temperature dependent. So whether you dope a semiconductor material or you are utilizing a pure crystal, both contains electrons as well as holes, and their product in a given material, which is n dot p, must remain equal to some constant Ni square. I already discussed in my previous lecture that even though we define Ni, that is intrinsic carrier concentration, to be a constant, but this constant is valid. The validity of this term constant is only at a given temperature for a given semiconductor material. If you change the material, even at the same temperature, this Ni value changes. And finally, at the bottom of the slide, I write that this equation holds true both for doped silicon as well as pure silicon. Let me define some terminology in thermal equilibrium, that is the temperature that you have chosen for your device. N designates the number of free electron concentration which you find in the conduction band. P is the number of free holes which you find in the valence band. Ni is the number of electrons in the intrinsic silicon material whose value at room temperature is 10 to the power 10. Let me emphasize once again, this value 10 to the power 10 for silicon holds good only for room temperature. If you increase the temperature, this value will no longer be a constant or same, it will be some other value at higher temperature. Because I've chosen room temperature to be my reference temperature, and also I've chosen silicon to be my reference material, so I shall be using this value from now on in my next few lectures, unless of course I state otherwise. Then you have the value for the electronic charge, which you appreciate is the same for both holes as well as electrons. And thermal equilibrium is a term that is defined when your material is not connected with any external source of the voltage, that is, no applied bias to the material or to the devices. In a minute, just a few minutes ago, I had used the term that your semiconductor material is placed at some temperature, and that temperature, reference temperature, I had called to be 300 Kelvin room temperature. Now at this temperature, electron as well as holes or the whole crystal sample is seeing or obtaining a certain amount of thermal energy. This slide shows you the value of the thermal energy that the crystal is seeing because of this temperature, and the electrons and holes which are so far at 0 Kelvin temperature are bound in their respective covalent bonds. Now these bonded electrons receive this thermal energy and they and the bonds will, some sufficient bonds will be broken because of gaining of this thermal energy. This process is termed as thermal generation of electrons as well as holes, and as I had written in the bottom of my slide, that this thermal excitation or thermal generation process or mechanism is highly temperature dependent. As you increase the temperature, more and more bonds will be excited and more bonds will be broken in a given silicon material, and hence enhanced thermal generation concentration will come into being. Again, a repetition of what I said, that intrinsic carrier concentration, that is the carriers which are generated thermally in pure material, is a function of is highly temperature dependent, and very few bonds are broken, as I explained in the previous 2 or 3 slides, that if there are 10 to the power 22 atoms per unit volume, then at room temperature only 10 to the power 10 bonds are broken. So this is not a very large number. In other words, what we are trying to say is, even though the process of thermal generation is breaking the crystal bonds, yet the very few, that is only 1 every billion atom of silicon has a broken bond. So it's not a big deal. What I'm trying to say is that we are not really trying to damage the original silicon structure by breaking the covalent bonds due to this thermal energy. So even though this thermal energy process, thermal generation process, breaking of the bond process is taking place continuously and is very important to us, yet it doesn't destroy the crystal structure. And finally, because of this thermal generation process, I use the term that is a very important mechanism, is a very important process. It is this very process which distinguishes silicon from insulators and from metals. Because of this thermal generation process, silicon now, or semiconductor materials for that matter, now become better conductor rather than insulator, because thermal generation gives rise to free electrons in the conduction band and free holes in the valence band. Of course, I should also mention another important factor or parameter. Thermal generation, as you just saw in the previous 2 or 3 slides, is highly temperature dependent. So is the generation process dependent upon the band gap. I'm sure you can visualize in your mind, greater the amount of band gap, the greater would be the energy required to shift an electron, bonded or bound electron, from valence band to the conduction band. Thus, we finally come to this slide and write mathematically, as we discussed just now, that in the pure or intrinsic semiconductor materials, because electrons and holes are created in equal number, therefore the concentration of electrons N should be equal to the concentration of the holes P, and therefore this concentration of holes and electron is termed as intrinsic carrier concentration in the pure material, and its value had been given at room temperature, which I again write at the bottom of the slide, which is 1.5 10 to the power 10 electrons and holes per cubic center, of course at room temperature. If you increase the temperature, this value would increase. It will no longer be the same. So even though, let me summarize again, even though we define Ni, that is the intrinsic carrier concentration, to be a constant, but this constant value is subject to variation if you change the temperature or if you change the material. By changing the type of the material, what we are trying to say is we are changing the band gap of the semiconductor material. Next important topic in today's lecture is the carrier concentration when the material has been doped, either by the fifth group impurities or by third group impurities. As you know by now, third group impurities, when added to silicon, the material is termed as p-type silicon. When the fifth group impurity is added to silicon, the material is termed as n-type silicon material. So doped semiconductor materials therefore would be characterized by n-type or p-type. There are two advantages of changing or doping the material, that is changing the pure characteristic of semiconductor material. When I say characteristic, I mean carrier concentration. Number one, in the intrinsic material, both electrons and holes are equal. Therefore, you have to deal with equal number of electrons and equal number of holes. Secondly, their carrier concentration is not that significant, is not that large, even though in absolute terms it seems large, 10 to the power 10. But yet it is not large enough to give you an appreciable amount of current to use the material as a good conductivity device, as a good, which gives you a large amount of conductivity. Hence, the doping process is done, or material is doped, for the following two reasons. Number one, you can enhance, you can increase the carrier concentration 1,000,000 times, and also you can change the type of the material, conductivity type, whether the conduction is mainly due to electrons or whether the conduction is mainly due to the holes. So a doping process, or doping the pure material, can give you two different phenomena. It enhances the free carrier concentration in a given material. It can make the material either the electron being in majority or the holes being in majority. So we use another important terminology for the doped semiconductor materials, which you see in this transparency. If the material is doped with the donor impurity comes from the fifth group of the periodic table. To our first approximation, we will discuss this carrier concentration and density of states in the next few slides. We can approximately say that the amount of donor added to the pure silicon crystal, the concentration of the donor impurity is equal to the concentration of the free electrons in the n-type material in thermal equilibrium. Now this term on the left side of your slide, NNO, now let me clarify this terminology. N stands for free carrier concentration of the electrons. Subscript N refers to n-type material and O refers to thermal equilibrium. So in thermal equilibrium, in a doped semiconductor material, n-type semiconductor material, the number of electrons, that is the concentration of electron, is designated as N, capital N being the concentration of free electrons in the conduction band. The subscript N refers to the type of the material, which is n-type, and O in thermal equilibrium. Now I must remind you the important condition, the condition of thermal equilibrium, or the condition of law of mass action, which states whether your material is intrinsic or your material is doped, n-type or p-type, the product of electron concentration, free electron concentration and free hole concentration, that is n dot p, must be equal to some constant Ni square. So I have written that the whole concentration, minority hole concentration, I'm using the term minority now. In the intrinsic semiconductor material, both electrons and holes were equal in number. So when they were equal, obviously, logically it follows you can't call one the majority and the other in minority, because they are both equal. But once the material has been doped, and according to our requirement, we have enhanced the concentration of electrons by choosing a dopant from the fifth group rather than from the third group, obviously the concentration of electrons will be much larger than the concentration of holes. So in an n-type material, or the material in which dopant has been added from the fifth group of the periodic table, the electrons will be termed as majority charge carriers, and thus holes will be termed as minority holes or minority charge concentration. Thus you appreciate the terminology NNO and PNO, yet the product of both of them must be equal to Ni square, which is the requirement of thermal equilibrium. The same applies on the right side of the slide for the p-type material. The only difference being, in the n-type materials, free electron will be in majority, and in the p-type material, free holes will be in the majority. The electron concentration will be almost equal to the donor concentration. For p-type material, the free hole concentration is almost equal to the ionized acceptor impurity concentration. Charge carrier, how do we mathematically express the law of mass action? I have written it down again for you to absorb it properly. Carrier concentration for an n-type material is subject to thermal equilibrium equation, which is NNO dot PNO. NNO refers to the electron concentration in the n-type material in equilibrium. PNO refers to the minority hole concentration in the n-type material, the product being equal to Ni square. This Ni square for silicon at room temperature would be 10 to the power 10, and numerically you can calculate how much hole concentration, that is minority concentration, would be if the donor concentration is known. So this is a very important thermodynamic equilibrium equation or thermal equilibrium equation, in which the minority carrier concentration or whole carrier concentration has to be evaluated. Another important equation that we have to keep in mind, that throughout the crystal, throughout the space or volume we are talking about, the requirement of space charge neutrality applies. What does that mean? That the total positive charges must be equal to the total negative charges. I will elaborate this condition of space charge neutrality in the following slides in a minute. I have now moved on that the same equations of thermal equilibrium and space charge neutrality apply for the p-type material as they did in the previous slide for the n-type material. Now, up to now, we talked about a phenomenon of thermal equilibrium in which electrons and holes, that is free charge carriers, were being produced, were being generated in the crystal by breaking the covalent bonds, and the energy was coming from thermal energy because the crystal is maintained in thermal equilibrium at some temperature T. The reference temperature would, in my lectures for the time being, would be room temperature, which is 300 Kelvin mathematically. But there is another process taking place simultaneously. To maintain, we had used the term, to maintain what we termed as thermal equilibrium. Let me try to explain this word equilibrium. Carriers are being continuously generated, of course, with a certain rate. We will term this rate as thermal generation rate. This thermal generation rate, as I mentioned many times in the last few minutes, is very sensitive to the temperature at which your device or your material is maintained, and secondly, the band gap of the semiconductor material. Obviously, you can visualize the smaller the band gap, easier it is for the electron to jump from valence band to the conduction band. The wider the band gap, the bigger the band gap, it would be difficult for the electrons to move from valence band to conduction band. That is, you require a larger amount of energy equal to the band gap energy. So thermal generation process is highly dependent or is very sensitive to temperature and the band gap of the semiconductor material. So this you understood, that is, you understood the thermal generation process moving, showing like upward arrows, bound electrons moving in the conduction band where they become free and leave behind a vacancy termed as hole. In this slide, what you see is another mechanism, another process taking place in the same silicon at the same temperature, which is the reverse of the process we talked about, which is the reverse of thermal generation process. That is, electrons, free electrons, now jumping or going back from the conduction band into the valence band. In terms of the bond or crystal structure, what you see is that free electrons again come and become and make a complete bond again, or become bonded again. So this process is termed as the electron hole recombination process. Mind you, another process to appreciate, another term to appreciate. Just as in thermal generation, electrons and holes were being produced in equal numbers, therefore we call this process as electron hole pair, electron hole pair generation process. Similarly, in recombination, electrons and holes will be recombining together. That is, you are eliminating, you are decreasing one electron and one hole, that is in pairs. So recombination takes place in pairs. Having talked about the number of electrons and holes in a given semiconductor material, whether pure or doped, the carrier concentration in both pure, that is intrinsic material, and doped, that is extrinsic semiconductor material, is subject to law of mass action. That is, the carrier concentration, the product of n dot p must be equal to ni square, and ni square, that is the intrinsic carrier concentration, in turn is highly temperature dependent and also dependent upon the band gap, and they vary. This dependence is exponential. Having discussed this charge density of free charge carriers, now we will introduce another term, which is the effective mass approximation, or the concept of effective mass. What is this concept of effective mass? Well, in the conduction process, if you can understand the conduction process in a very simple manner, visualize an electron moving under the influence of an applied electric field from point 1 to point 2. So the electron moves from point 1 to point 2, taking a certain time t. So you can use the basic laws of applied mechanics, Newtonian mechanics. You can calculate the force experienced by this electron when it is placed in an electric field, and hence you can calculate the current being generated by the motion of this charge carrier, the motion being subject to this applied electric field in our case. So this is termed in very simple terms as conduction or conductivity of the semiconductor material. But there is another thing that you have not thought about. That electron has a charge, negative charge, which I mentioned, whose value I had given in the previous slide. It also has a mass. The electron mass you are familiar with is designated as m naught, which is the mass of the electron in vacuum. So what is your Newtonian mechanics? Your Newtonian mechanics tells you that the force which the electron, whose charge is q, experiences when it is placed in an electric field termed as E, then the force would be equal to mathematically q into E. Q being the charge of the electron, which is negative in our case, negative in the case of the electron, E being the strength of the applied electric field. This force, according to Newtonian mechanics, will produce acceleration experienced by this electron, which is moving in an electric field E, and that force is m, the electron mass, into A. A is your acceleration. So this is your famous or very well known Newtonian mechanics. F is equal to m into A. It is this m which has to be modified now, because the electron is not moving in vacuum, which you are used to imagining. This electron, now your electron in semiconductor, is moving in a real crystal. Each crystal has its own characteristic dielectric constant. So how come this mass changes, or what do we do with this mass now? Do we use the same mass, m naught, which was called previously as the electron mass in vacuum, or do we change this mass because now the electron is moving in a real crystal? Mind you, when I use the term real, I have the following terms in my mind. The semiconductor crystal has many different obstacles with which this electron can collide and therefore cannot accelerate as is imagined or as is expected by using the simple Newton's law, F is equal to m into A. These obstacles being, first of all, the ionized donor and ionized acceptor impurities, any impurities other than donor or acceptors, and defects in the crystal structure, so on so forth. There can be a large number of so-called scattering centers within a real crystal in which the electrons can collide while moving subject to the electric field. Thus, what happens? The electron does not accelerate as envisaged in our Newtonian equation. Therefore, what do? We modify the mass of the electron from m0 to some other mass in real crystal, in the semiconductor crystal, and this is termed as the effective mass approximation, or the concept of the effective mass. Finally, I have written at the bottom that not only we want to apply, we have done this, we have used this approximation in order to be able to use the Newtonian mechanics, but we also want to understand this concept of the effective mass when it is applicable to electrons moving in materials from which we have fabricated various devices, semiconductor devices. Again, I have tried to explain the concept of the effective mass in using rather fancy idea in this slide. What you see on the left side of the slide is that the free electron is moving in vacuum, whose mass in units is given as 9.1 into 10 to the power minus 31 kg. I'm sorry, I forgot to write kg with this figure. This is the free electron mass. When I say free electron mass, I mean the mass of the electron when it is moving in vacuum. And then at the bottom of the box you see now the electron we are talking about, that is the electrons which are moving in real crystal, my crystal being the silicon crystal. In silicon crystal, I'm not going to use the mass m0, which is the mass in vacuum, because as I just explained, if the electron was moving in vacuum, it would continuously accelerate subject to the condition of F is equal to Q into E, obeying the laws of electrodynamics. Now its mass has been replaced by another mass, m star, which is called the effective mass. And so even though the electron is making many collisions, whenever it encounters an obstacle, as I just mentioned, there is a long list of these obstacles, the ionized donor and acceptor impurities, some other impurities other than donor or acceptor, crystal defects, so on and so forth, but yet the electron moves wherever it can, obeying F is equal to ma, the Newtonian mechanics is subject to. So thus, even though, to sum it up, what I'm trying to say is, even though the electron is moving in a structure which is full of obstacles with which the electron scatters or undergoes collision, yet two basic laws of electrodynamics and Newtonian mechanics are applicable wherever they can. Okay, so we move on after making this simple approximation known as effective mass approximation. So we are good now to use two equations, which is F is equal to Q into E, E being the direction of, E being the electric field, F being the force, Q being the charge of the electron. In the case of the electron it will be minus Q, for the case of the holes it will be plus Q. So accordingly you can calculate the force, direction of the force which the electron will experience, and the direction of the force which the hole would experience when it is placed in an electric field E. These are the few slides which I thought you might be interested in using some simple laws of quantum mechanics. How to express this effective mass in terms of the wave-like properties of the electron, because as you appreciate, electron behaves as a particle having a mass m0 as well as a wave having a wavelength lambda. So I use these fundamental relationship in order to explain certain energy associated to the electron when it is moving in a real semiconductor crystal under the influence of the electric field E, which we just talked about. This transparency, this slide actually is a revision of what we had learned in our previous studies at high school level. This is simple quantum mechanics, simple laws of wave particle nature of the electron. Thus, the electron mass can be explained in terms of the wave-like properties which I have shown at the bottom of the slide. This relationship can be calculated very easily using the simple relations shown in the last two slides. So this formula gives you the effective mass of the electron inside the crystal, where capital E being the energy associated with the electron, K being the wave number, which is 2 pi by lambda, lambda being the wavelength which the electron has while moving in the crystal, m star being the effective mass. So m star, the effective mass, is in this, according to this equation, now is related to the wavelength of the electron in a given crystal. Let's try to understand these few relations or last two slides in terms of schematic illustration. What you see at the bottom of the slide is that the electron is moving, because I've chosen the n-type to be my reference material, n-type doped, n-type, that is donor doped crystal at room temperature, and the crystal being silicon. So I'm using silicon at room temperature, which is n-type. So in an n-type silicon crystal at room temperature, the electron moves, as you see at the bottom of the slide, opposite to the direction of the applied electric field E. Why opposite? Because of its conventional direction, because of its negative charge. At the bottom you see positive donor, ionized donor impurity. So the electron, while moving in an electric field subject to the Newtonian mechanics, F is equal to m into A, encounters collision with the ionized dopant impurity present in the crystal. You have yourself doped the material, you have yourself added donor ions into the semiconductor crystal. Well, they stand ionized now because the crystal is at room temperature. So at room temperature, most of the, or in fact all of the, to a good approximation, all of the added donor ions are ionized. So the donor ions, the positive donor ions, are present because you doped the material yourself with a donor impurity in order to enhance or increase free carrier electron concentration. Okay, so these electrons, while moving, would undergo collision, would undergo scattering due to these ions present inside the crystal. So it's no longer, electron is no longer accelerating because of the presence of these scattering centers. So the top bullet says the electron is subject to internal forces from the lattice, which is ions and core electrons, and external forces such as electric fields. I just explained this. The electron has to undergo acceleration because it sees a force due to an applied electric field It also sees forces due to positively ionized donor atoms and negatively ionized acceptor atoms, and so on and so forth. And finally, in a crystal lattice, the net force may be opposite the external force. Okay. So, however, the net result is that the electron still manages to undergo acceleration, but only during the interval of space, only during a certain space in which the electron does not make any collision. So I can write down mathematically a relationship which was explained in the previous slide, that now electron is subject to two forces, one arising due to an applied electric field, and the force is designated or termed as F external and F internal. Internal forces due to scattering centers present inside the crystal, and now we use the electron effective mass m star. So we come up with a very simple relationship, F is equal to m into a, that is acceleration now is due to two forces present, one the applied force in terms of the potential connected across the material or device, and secondly the forces present due to the ionized impurity centers, and the effective mass has been used to replace the mass of the electron in vacuum. So having made this simple approximation and using the quantum mechanical relationship of the electron, we move on further. So now you have to calculate the energies of the electrons, which is required, the energy which is required to free the electron when they are bound within the covalent bonding. And hence, if you recall your lecture number 1, in which I had shown that the electron in the hydrogen atom is bound with the energy, with a formula given as the energy of the electron in the hydrogen atom. I use the same relationship which we used in calculating the energies of the electron in isolated single atoms. We use the same terminology, we use the same expression for calculating the energies of the bound electrons in semiconductor crystal as well. The only modification in our concept would be that the electron is now not moving in vacuum, it is now moving in a dielectric of the silicon crystal, and it is bonded in a covalent bond now, and the electron mass has been replaced with an effective mass m star. So you see in this slide the modified formula which we had borrowed from understanding of the electron in the hydrogen atom, and hence I use the term hydrogenic model in the next slide. And the interesting thing that you would appreciate from the top equation is that the dielectric now has been modified as well. Not only the electron mass has been modified, the dielectric constant of free space has also been modified. So we use two terms, epsilon 0 and epsilon s. Psi stands for semiconductor material, dielectric of the semiconductor material. And the interesting thing to appreciate in this relationship is that the dielectric is in the denominator and it is a square term. So the energy of the electron, of the valence electron in terms of the hydrogenic model, now has been reduced approximately 100 times as compared to the energy of the electron in the K shell in the hydrogen atom. So the bottom portion of this slide shows that the binding energies of the electrons bonded in their respective covalent bonds, they come out to be, for phosphorus, comes out to be 0.045 electron volt, and for gallium it comes out to be 0.072, all the energies being in the units of electron volts. This is something to appreciate at this point, that the energies which the electron now require to break their bonds, that is to make the electrons free, and imagine it to be residing in the conduction band of a silicon crystal, the energies are so low as compared to the electron energy in the isolated hydrogen atom. They have been reduced so much. They are order of only milli electron volts as compared to electron minus 13.6 electron volt required in the hydrogen atom. And this energy, as you would recall, is now almost comparable to the energy which is available to the system, which is available to the silicon crystal at room temperature. That value was 0.025 electron volt. Hence the term that we had been using all along, that at room temperature almost all the added impurities or the dopant impurities stand ionized. They are already ionized because we require only this much, this small energy, which is easily available to us, to the electrons in silicon crystal. We come to another interesting concept, having talked about the number, that is concentration of free electrons and concentration of free holes in the doped semiconductor crystal. Next we come to the concept of density of states. What is density of states and what do we mean by Fermi-Dirac distribution function? Let me go back again to the previous slide. I'm using two terminology, density of states and Fermi-Dirac distribution function. What do I mean by density and what do I mean by states? Well, first word density simply refers to the carrier concentration per unit volume, which in our case we take to be centimeter per unit centimeter cube. And states, because according to quantum mechanics, subject to the laws of Pauli's exclusion principle, because electrons are fermions, let me elaborate. Those particles who have intrinsic spin to be half h cut, they are termed as fermions. Because electrons being fermions, therefore they are subject to Pauli's exclusion principle. Therefore, not all the electrons can reside in one energy level or one energy states. They have to be distributed in various states subject to the laws of quantum mechanics. They must have discrete energy states and they must obey Pauli's exclusion principle. So we have to be very careful in talking about the energy states of free electrons as well as the energy states of the free holes, because we have to distribute these electrons. There are many free electrons now in the dopant crystal, as large as 10 to the power 16 per cubic centimeter, and there are so many electrons now in doped crystal. So we have to be careful that we do not violate the law of quantum mechanics, okay, while determining or calculating their energy states. Before I go into detail of what Fermi-Dirac distribution function says, let's try to understand what we talked about before. How many electrons, free electrons there are in an n-type crystal. To repeat once again, majority carrier concentration can be approximated by the density or concentration of the added impurity. That is, free electron concentration in an n-type semiconductor crystal is almost the same as the donor impurity that you added. Minority concentration is temperature dependent, because let me explain this middle point. Thermal generation is taking place simultaneously all times. You have doped the crystal. Now in a doped or extrinsic semiconductor material, the thermal generation process is also taking place, because your crystal is now in thermal equilibrium. The entire crystal is in thermal equilibrium at a certain temperature T, and the process of thermal generation is continuously taking place. It hasn't stopped due to the dopant process. It hasn't stopped in a doped or extrinsic semiconductor material. So what I'm trying to say is that even in the doped or extrinsic semiconductor material, the process of thermal generation rate is the same, is continuously taking place as it was in the intrinsic or pure semiconductor material. So electron and hole are continuously being generated subject to a certain or characteristic generation rate, which I mentioned before many times. This rate is dependent upon temperature. This rate is dependent upon the band gap, because we have for the time being chosen silicon, so band gap remains the same because we have chosen the temperature, reference temperature, to be room temperature. So both the band gap Eg and the temperature 300 Kelvin for the time being in our discussion is the same. We are not varying yet unless we decide to do so. So thermal generation rate is taking place at the same rate as it was in the intrinsic semiconductor material. This thermal generation rate is now creating electrons and holes in equal number, as we explained many times before. But the thermally generated electrons now are not in such a large number compared to the free electrons that you obtained or that you got from doping process, from the ionization of the dopant impurity. So the thermally generated electrons are only a minor fraction of the electrons that you got from the dopant impurity. However, the whole concentration now is mostly due to the thermally generated holes. So the minority carrier concentration therefore can be exploited by enhancing the temperature. Or in other words, you can understand it like that as we increase temperature, the effect on the enhancement or increase in the minority carrier concentration would be larger than on the majority carrier concentration. Thus I say minority carrier concentration or minority carrier density is strongly affected by temperature, unless we increase the temperature so high that even the majority carrier concentration gets affected, and thus the material will be at a very high temperature. The material would start, the dope material, the extrinsic material would start to behave as an intrinsic material again, but that takes place at a very high temperature. Okay, which I have explained at the bottom of the transparency. Finally, what I would say is that to obtain carrier densities, let's investigate the distribution of charge carriers over the available energy states. Let's try to understand these last two lines. I just mentioned that the electrons in free electrons and free holes in silicon crystal are subject to laws of quantum mechanics. The energies must be discrete and they should obey Fermi-Dirac distribution function. So to obtain carrier densities or to carrier concentration, we have to investigate the distribution of charge carriers over available energy states in which electrons and holes can reside. To do so, we need some help from statistical methods. The classical particles, as you would recall, are subject to Maxwell-Boltzmann distribution, and photons having spin 1 are subject to Bose-Einstein statistics. Electrons, as I just mentioned, are fermions. Fermions is that group of particles, is that class of particles who have or which have spin half edge cut, and they are subject to Fermi-Dirac distribution or Fermi-Dirac statistics. So the statistics that we use in order to calculate the density of electrons and holes in a given semiconductor material is subject to laws of Fermi-Dirac distribution. This Fermi-Dirac distribution is expressed mathematically in the following manner. I'm sorry, this is rather it involves a little intuition, and I'll try to explain it in a slightly intuitive manner. If an electron tries to gain energy, if initially the electron was in some energy state E1 and it tries to gain or go to a higher state energy level designated as ET, then the number of electrons in state E1 is called N1 and number of electrons in state E2. So the electron concentration in energy state E2 and the electron concentration in energy state E1 is subject to this exponential distribution function, which is termed as Maxwell-Boltzmann distribution function, and it comes out to be approximately equal to e to the power minus delta E over kT, where delta E is the change in energy for the electron in going from state E1 to state E2 at some temperature T, and this in short in abbreviated form is termed as the Boltzmann factor. Later on you will come to see that in most of our mathematical calculation in semiconductors, this Boltzmann factor arises wherever appropriate in different forms. What different factors or what different parameters this Fermi-Dirac distribution function takes into account? They are listed. There are two fundamental ideas that we must take into account. The first is, as I mentioned earlier, electrons have particle-like nature as well as wave-like nature. Wave-like nature comes into being, the concept of wave nature associated to the electron comes from the requirement of quantum mechanics. And secondly, that the electrons, one electron is not distinguishable from the other electron. So all the electrons, the free carrier concentration, the electron free carrier concentration, and thus the free hole concentration are indistinguishable. And secondly, the Pauli's exclusion principle demands or states no two electrons can occupy the same energy state. It's the same concept that we used for the simple Bohr's hydrogen atom, or atoms heavier than hydrogen atom. Hence, keeping in mind the quantum mechanics, the discrete energy states or discrete energy levels of the electrons in semiconductors, and that they are fermions, we move on further. We must apply these two characteristics of the electron in semiconductor crystal in going further. Thus, the energy distribution of electrons in solids obeys Fermi-Dirac. The statistics of Fermi-Dirac distribution function is expressed as F into E is equal to 1 over 1 plus E, where EF is the Fermi energy and E is any energy associated with the electron, and T being the room temperature, which I have taken to be room temperature, where T being the temperature of the semiconductor crystal, which can have any value, but for my lecture, for the time being, it is room temperature. What is Fe? As you see in this equation, E is any energy which we can elaborate, which we can choose. EF is a special term which is termed as Fermi energy. Let's understand this Fermi energy or Fermi-Dirac distribution function. The function Fe, the Fermi-Dirac distribution function, gives us the probability that an available energy state at E will be occupied by an electron at absolute temperature T. In simple language, this function Fe will give you the probability whether the electron is occupied by some energy state or some energy state is occupied by an electron or not. Well, this is a new terminology which we have introduced now at this point in our lectures. Because electron energy states are quantized, the result, the interpretation of quantum mechanics, that each electron will have some discrete value or discrete level of energies. Now these levels can be, the electron may be in those levels or those levels may be free. So if some discrete energy level has an electron in it, or the electron or the state is occupied by an electron, so Fe, the Fermi-Dirac distribution function, in fact gives you the probability whether a given discrete energy state is occupied by electrons or not occupied by an electron. If it is occupied by electron, it gives you the probability of occupation of electron. If it is empty, that is whole. Then you say a hole is present. Okay, the quantity EF is called the Fermi level, and the Fermi level is that energy at which the probability of occupation of an energy state by an electron is exactly half. That is, FEF is equal to half. Now let's combine the top two statements again. FEF is a function of some energy EF, Fermi energy EF, and small f the function. This F into EF gives you the probability, a certain probability, that the electron is there or not there, or whether a given energy state EF is occupied or not occupied. But if this probability comes out to be exactly equal to half, that is the concept of Fermi energy EF. So capital E with a subscript F, EF, is that energy level at which the probability of finding the electron is half. The Fermi-Dirac distribution function is symmetrical around the Fermi level EF, and for intrinsic Fermi level EI is equal to EF. In other words, EF will be in the middle of the band gap. If the materials are doped, then we see that the Fermi energies that are several kT units above or below Fermi level, the Fermi-Dirac distribution function can be approximated by this. We have tried to slightly approximate the Fermi-Dirac distribution function, which I showed you in the previous slide, that if the energy is associated to the electron are much greater than the Fermi level, then the formula approximates to the top of the equation, and if energies are less than the Fermi energies, then it is approximated by the bottom equation, and the bottom equation actually gives you the whole probability, which I mentioned before. If the electron is not there, if a given energy state, Fermi energy state, is not occupied by electron, which means it's empty, which means it's the probability of holes. Thus, Fermi-Dirac statistics or Boltzmann statistics for energies holds for energies which are much greater than kT. That is, we are talking about those energy levels associated to electrons which are greater than thermal energy. Thermal energies now being our reference energies. Now I will try to solve the electron concentration using the Fermi-Dirac distribution function, which we just talked about. So the total number of electron concentration, the number of electrons per unit volume in the free electron concentration, mind you, the free electron concentration in the conduction band therefore can be calculated from the top equation, because electrons are now residing in the conduction band, and the conduction band expands from some energy, bottom energy level, which we will designate as the lower value of the conduction band, to some top part, n into E being the density of states, that is the number of states within the conduction band, and function FEE, because Fermi-Dirac distribution function is the one which gives you the probability of finding the electrons in some given energy states. And as I explained before, where these states are, obviously these states are going to be in the conduction band. The conduction band starts, the edge of the conduction band is now designated as EC. So the states now range from EC higher up within the conduction band, and capital N as a function of E being the density, the total number of states that you can have within the conduction band, and if they are filled, F into E. So we integrate this probability distribution function, and we get the total number of electrons. Similarly, we can calculate the whole total hole density, that is the total number of concentration of free holes in the valence band, by using the same Fermi-Dirac distribution function, but here it will be 1 minus Fe. 1 minus Fe signifies that now the states are empty, they do not have electrons in them. What do they have? They have holes. So by using these two simple relationships, we can calculate the free carrier concentration of electrons as well as holes by using the laws of Fermi-Dirac distribution function, subject to two main conditions which have been derived by using keeping in mind the quantum mechanics and Pauli's exclusion principle. I express the same relationship in a slightly different manner. This transparency should be retained in your memory for future lectures. So you must appreciate that the electron concentration N is dependent upon the intrinsic carrier concentration and is exponentially dependent upon temperature kT, thermal energy kT. And For a degenerate semiconductor material, I mentioned this terminology before, non-degenerate and degenerate. So far our discussion has rested upon a dopant concentration which does not destroy the basic crystal structure, the basic parameters of our host silicon crystal. That is, the concentration has been deliberately kept so low, of the order of, in silicon, let's say 10 to the power 15 or 16, which is 1 part per million or maybe 1 part per billion of dopant impurity. But if the impurity exceeds, if the crystal is highly doped, so highly that the donor and acceptor term increases to a level of 10 to the power 19, then there will be a large concentration of electrons and a large concentration of free holes, and the simple laws of Fermi-Dirac distribution or Maxwell-Boltzmann equation, which we had tried to use for silicon, will no longer hold, and we will have to use some other relationship for such high dopant impurities and such materials which are doped with such a large concentration, therefore are termed as degenerate semiconductors. So once again, degenerate semiconductor are those in which the dopant impurity or the free carrier concentration exceeds 10 to the power 19 for silicon at room temperature. In future, such material will be termed as highly doped. Highly doped materials are not a bad thing. We use highly doped materials, as you will see in future lectures, for fabricating, for other operations known as Zener diodes or avalanche diode, where high dopant is required. Now, the same repetition of the important assumption that we made, that the carrier concentrations are subject to an important equilibrium condition, which is also known as the law of mass action, and that is P dot n is equal to Ni square. Now, P dot n is equal to Ni square, we used this equation in the early part of the lectures too, but now we can correlate this with another exponential term, because now we understand that the energy states of the electron are subject to or are calculated by using the laws of Fermi-Dirac distribution function, hence another expression for the equilibrium condition or another expression for the law of mass action. Again, you appreciate at the bottom that the intrinsic carrier concentration is highly temperature dependent and dependent upon the band gap, exponentially dependent. I also mentioned that even though you have increased the electron concentration many folds, which means you understand as if you are trying to increase a negative charge in an n-type material, or you are trying to enhance or increase a positive charge in a p-type dope material. Yet you have to keep in mind that even though you have increased the electron concentration, even though you have increased the hole concentration by adding donor impurity or acceptor impurity respectively, yet the important condition or the important law of space charge neutrality holds or is applicable, whether it is neutral, it is intrinsic material or doped semiconductor material. I have mathematically written it down for you to understand what do we mean by space charge neutrality. The top equation says that the total charge density in a given material, in a given n-type material, is 0. The total charge density is also 0 in a p-type material as well. What does that mean? That means if the semiconductor material is n-type, it contains a large number or majority electrons. It also contains holes, they will be in minority. So in an n-type semiconductor material, the majority carriers are electron, the minority carriers are holes. The negative charge will be large due to large number of electrons. The positive charge of the holes would be small due to positive charge concentration of the holes. Then there is a large number of donor impurity. The donor impurity is positively ionized. Acceptor impurity in the ionized state is negatively charged. So we have two types of charges, the positive charges and the negative charges. Let's look at the third equation. Space charge condition requires that the total positive charge must be equal to the total negative charge. I'm using the word total. What does that mean? It means the positive charge is coming from two different types of charges. One, holes are positive, the positive holes, and second, the donor impurity is positively ionized. So donor impurity is contributing towards positive charge, the holes are contributing towards positive charge. Mind you, you must appreciate they both have positive charges, yet when their motion is considered, holes are termed as mobile because they can move easily. Donors will be termed as immobile because they are as massive as an atom. Is simply one electron has been removed. So positive charge due to immobile donor ions, positive charge due to mobile holes. So total positive charge must be equal to total negative charge. The negative charge is being contributed due to mobile electrons and due to immobile negatively charged acceptor ions. So the net result is that n dot p, we know that law of mass action, n dot p is equal to ni square is applicable. Having said that, we can arrive at the following simple relationship by using the expressions of the free charge carrier concentration that we derived using the law of Fermi-Dirac distribution functions. So the most important relationship that we would be using in further calculation is that now the electron concentration is the one which we obtain by the net concentration of donor ions minus the acceptor ions. That is, the total negative charge must be equal to the donor concentration minus if there is any acceptor concentration. Similarly, the whole concentration in a p-type material can be approximated to be equal to the acceptor concentration minus if there is any donor concentration. So therefore, the minority concentration, minority holes in an n-type material, is given by ni square over nd minus na. Similarly, for the minority hole concentration in the p-type material. So these are the few most important relationships that we obtained for carrier concentration by using the Fermi-Dirac distribution function and by using the condition of space charge neutrality. These relationships, these last two relationships giving you the carrier concentration, are the basis of our carrier concentration that will be used later on when we discuss device operation under equilibrium and under non-equilibrium conditions. So we have formed a basic basis of carrier concentration relation. Well, so far I've been talking about the carrier concentration, but yet I have been I've been emphasizing on the fact that carrier concentration is highly temperature dependent, exponentially in fact, because now you have a mathematical relationship. Let's talk a little bit more about this temperature dependence of free charge carriers in semiconductors. Let's imagine it as follows. Your material has been now doped, and I have taken my dopant to be from the 5th group because I want to make the material n-type. Let's hypothetically begin with the 0 temperature, as you see in this diagram of free carrier concentration versus temperature. Let's hypothetically take the scale, begin the scale from 0. At 0 temperature, all the dopant impurity will be so-called frozen, will not be ionized, because you require some minimum amount of energy. We calculated this energy before in the slide titled hydrogenic model, or the energies of the electron using the approximation of effective mass in the same equation which we use for calculating the energies of the electron in the hydrogen model. So at absolute 0 temperature, or some temperatures very close to 0, all the dopant impurities will be neutral. The covalent electrons would still be bonded with their parent atoms, will still not be free. But as we start to increase the energy, increase the temperature, the thermal energy would increase, and if it becomes comparable to the ionization energy of the 5th valence electron, which is not large, mind you. You recall it was only about 50 milli electron volt. So if we reach a temperature comparable to this energy, all the dopant impurity that you have added will be ionized, and the term we use is that the impurity stands ionized. All the dopant added impurity stands ionized. So the carrier concentration would increase linearly as the temperature is increased from 0 to some temperature at which the atoms begin to ionize. When the temperature is very low, some of the dopants are not ionized. At very low temperatures, some of the dopants, even though the ionization has started, but not all the impurities ionize. They are slowly beginning to ionize. You are slowly getting few and few free electrons in the conduction band at very low temperatures. So at low temperature, the material is said to be, or the stage is called as the freeze out stage, or the stage at which the impurity is just beginning to ionize. And then as the temperature is increased, let's say some value from 200 to 300 Kelvin, that is, we are approaching the room temperature, all of the added impurity stands ionized. And if you increase the temperature further, whatever donors you have added, they already ionize. There are no more donors to be ionized. Hence, your graph will be flat. You are increasing the temperature, yet the carrier concentration remains constant, because all the donor atoms that you added have already been ionized. So this range of temperature is termed as saturation range. Now you go on increasing the temperature further. What is now happening? Because all the donors that you added have already been ionized. But remember another process that we talked about, that is taking place continuously, and with the increase in temperature, it increases the concentration of free charge carriers in equal number, in pairs, exponentially, and that process is the thermal generation pairs, thermal generation of electron and holes in pairs. So at very high temperature, the thermal generation process creates free electrons in the conduction band, which approximately become equal to the concentration of the dopant impurity that you have added. In simple terms, there is a concentration, there are electrons which is equal to dopant impurity, and now you have added an equal amount of electrons coming from the thermal generation process at very high temperature. So the material becomes intrinsic again. The material, I'm sorry, I should not say that the material becomes intrinsic. It has not become intrinsic. It behaves as if it is intrinsic again, but at very high temperatures. So that is what has been tried to, that is what I have tried to show in this transparency. The variation of electron concentration with temperature, and the significant feature is the intrinsic region at high temperatures, where the carrier concentration rises exponentially and the material starts to behave as if it is intrinsic again. So I will repeat once again that you start off with an intrinsic material and you dope it with a, you start off with a intrinsic material at a given temperature. Then you can enhance the carrier concentration by doping a particular impurity. So the carrier concentration increases and the material is no longer intrinsic. Let's do the following two processes. Increase the temperature of a material which is now extrinsic, which is now doped at high temperatures, as this slide demonstrates, as this slide tries to show you, both schematically with the help of a diagram as well as the text, that carrier concentration increases exponentially. The majority carrier concentration increases, the whole concentration as well as the electron concentration increases exponentially due to thermal generation process, and the electron concentration created in thermal generation process becomes comparable to the electron concentration coming from the dopant impurity. So your doped, your extrinsic material is now behaving like an intrinsic material. This was one way of changing the characteristics of a doped extrinsic material to that of an intrinsic material at very high temperature. The other mechanism is the counter doping. You keep the temperature same, room temperature for example. Do not increase the temperature to very high values, which I call them, let's say the high temperature for silicon is around 450 to 500 Kelvin for silicon. Keep the temperature room temperature. Counter dope the material. What is counter doping? You added 10 to the power 16 donors. Now you add the same amount of, same concentration of acceptor impurity. What is the net result? The electron concentration from the dopant impurity now is equal to the whole concentration coming from the added acceptor impurity. This process, this mechanism is termed as dopant, counter doping. So the interesting observation is that your intrinsic material at high temperatures, your doped material, your extrinsic material at high temperatures starts to show characteristics of an intrinsic behavior, shows an intrinsic behavior. And there is another mechanism of counter doping in which your doped material, previously doped material, now by counter doping also starts to behave as an intrinsic material. So this is another interesting feature by which you can exploit or control various characteristics, various parameters of a doped semiconductor material by using high temperatures and by using the phenomenon of counter-doping. Another transparency showing you the same thing which we talked about just now, that is how the Fermi level vary with temperatures. Let me explain this slide in a very simple language. Here is the band gap. If your material is pure, the intrinsic Fermi level will be exactly in the middle of the band gap. This is the conduction band and this is the lower valence band. And between these two bands, at midway level, will be your intrinsic energy level. Now you dope the material N-type. The Fermi level will now shift in the upper half of the band gap between intrinsic level and the conduction band, lower edge of the conduction band. It will be somewhere in the middle of the half, on top of, somewhere in the upper half of the band gap. And for P-type, it will be, the Fermi level would be in the lower half of the band gap. Go on increasing the dopant concentration. When we increase the dopant concentration, the Fermi level shifts and goes close and close to the edge or bottom of the conduction band. For high dopant acceptor impurity, the Fermi level shifts downward. Okay, that was if you change the dopant concentration. Now let's keep the dopant concentration constant for a given extrinsic material. Just vary the temperature. Don't change the don't change the dopant concentration. Increase the temperature. What does happen when the temperature of the semiconductor material is increased? More and more thermally generated electron hole pairs are being created, and they are being created in equal numbers because we use the term electron hole pair generation, thermally generated electron hole pairs. This thermal generation enhances the majority carrier concentration. It does not make the majority carrier concentration significant, does not change the majority carrier concentration significantly. However, the minority carrier concentration now gets increased to a large number. The end result will be your material starts to become intrinsic, and that's what happens to the Fermi level. It starts to shift downwards and almost comes close to the intrinsic energy level EI, somewhere in the middle of the band gap. That is an important effect of increasing the material temperature, that now your Fermi level is shifting to the middle of the band gap as the temperature is increased, and because of the temperature enhancement, the material is trying to show or exhibit the characteristic of an intrinsic material. So maybe this is a good time to stop at this point, and in the next lecture we will be talking about another important mechanism which I mentioned many times so far, the opposite mechanism of recombination, in which free electron and free holes are recombining just as free electrons and free holes were being generated thermally. Okay, so we talked a lot about free charge carriers in semiconductors, elaborating not just on their carrier concentration but also taking into account their energy levels subject to the laws of quantum mechanics, and hence finally using the Fermi-Dirac distribution function. And we got some very important relationships for the carrier concentration of electrons as well holes expressed in terms of the Fermi energy level EF. We also talked about the important relation of the temperature dependence of the free carrier concentration in semiconductors. So finally, we can summarize all this, what we talked about in the last hour or so. Starting with the very simple understanding that thermally generated electrons and holes, whether the material is pure or whether the material is doped, requires at room temperature some energy, which is even though much smaller than the band gap energy of silicon. Band gap energy of silicon for room temperature, which is 300 Kelvin, is 1.12 electron volt. Let's call this figure approximately as 1 electron volt. So even though the band gap of silicon at room temperature is about 1 electron volt, even though the energy is much smaller that the covalent bonds receive at room temperature, yet there is a significant thermally generated electron hole pairs in silicon crystal. So at room temperature there is a finite concentration of electron and holes present in silicon, and this concentration is approximately 10 to the power 10 electron volts, even though a large number, yet not so significant in terms of the crystal atoms present in the host crystal. Then we summarize that in pure silicon crystal, conduction electrons and holes are formed in pairs, as I just said, coming from thermally generated thermal generation process. Holes are considered as positively charged particles present in the valence band, and electrons are present, negatively charged electrons are present in the conduction band. The negatively charged electrons are present in the conduction band, and both these electrons and holes do take part in the conduction process. Having completed this lecture and having talked about the strong temperature dependence of carrier concentration, we can now summarize our result in the following manner: that the band gap energy of silicon at room temperature is roughly 1 electron volt. Even though this is a large amount of energy for a band gap, even though the band gap energy is large enough, and the thermal energy that the electrons that the crystal receives at room temperature is very small, yet at room temperature there is a significant number of free charge carriers present coming from thermal generation process. And in pure silicon crystal, therefore, you will have some free electrons in the conduction band and some free holes in the valence band, which are coming from thermally generated electron hole pairs. So thermal generation mechanism or thermal generation process gives rise to free electron and free holes even in the pure crystal, which has not been doped so far. When you dope a silicon crystal by adding dopant impurity to make it extrinsic, or to make it n-type, or to make it p-type, then appropriate dopant is chosen either from the third group of the periodic table, which will make the material p-type, and the ionized impurity is termed as acceptor. And if we make the material n-type, the dopant impurity is from the fifth group of the periodic table, and it is termed as the donor, and the resultant impurity will be positively charged ionized donor atoms. And finally, we would like to conclude that the carrier concentration can be controlled by choosing an appropriate concentration of the impurity, as well as by enhancing the device temperature. So the device temperature T the carrier concentration Na and Nd, and the band gap, characteristic band gap of a given semiconductor material. These three parameters can be selected according to the operation of a device that we want to use, and hence we end our lecture at this point, and we'll continue other important topics in the following lectures. Thank you so much for being attentive, and I do hope that you are beginning to understand the basic and fundamental concepts of semiconductor materials, of charge carrier concentration. Later on, these concepts will be employed in fabricating the devices, in understanding the physical processes of the device operation. Thank you so much, and I look forward to seeing you in the next class. Khuda Hafiz.